Good morning, one and all. I'm Sherry Ann Sacharias, Assistant Professor in the Department of EC at Rajagiri School of Engineering and Technology. Today I will be discussing on image compression techniques. This is a topic that comes under the Module 6 of the course Digital Image Processing. The contents of this presentation are as follows. We will start with the basics of dictionary-based compression, and we will look at an example of a dynamic dictionary-based algorithm. Then we will discuss on the basics of transform-based compression. We will also look into image compression standards such as JPEG and for moving pictures MPEG. After that, we will look into the basics of vector quantization and wavelet-based compression. Now, what is dictionary-based compression? In this compression technique, a dictionary or a lookup table which consists of a set of predefined words is used. So the word to be transmitted is first compared with the available patterns in the dictionary. And if a match is found, then the corresponding token or index corresponding to the word is transmitted. So using this index at the receiver side, the receiver will refer the same dictionary in order to decode the original word. So dictionary-based compression can be of two types, static or dynamic. So in a static dictionary-based compression, the dictionary values are predefined and they cannot be altered. Whereas in a dynamic dictionary-based compression, the dictionary values will be updated every time a new pattern or word is encountered. Dynamic dictionary-based algorithms are of three types, LZ77 and LZ78. They are also known as the Lempel-Ziv algorithms. So in the LZ77 algorithm, this is also known as a sliding window technique. The dictionary consists of a set of fixed length phrases. The LZ78 is a modified version of the LZ77 algorithm in which instead of using fixed length phrases, it builds phrases one symbol at a time, adding a new symbol to the existing phrase whenever a match occurs. The LZW or the Lempel-Ziv-Welch algorithm, this is another modification of the LZ78 algorithm. So in this lecture, we will be focusing on the LZW technique. The LZW algorithm is an example of a dynamic dictionary-based compression technique. So this is an error-free or lossless compression technique that addresses the problem of spatial redundancies in an image. Spatial redundancies refer to the fact that pixels in an image show a high degree of correlation or similarity with the neighboring pixels. So in the LZW coding, a fixed length code words are being assigned to a variable length sequence of source symbols. The advantage of LZW algorithm over arithmetic coding or Huffman coding is that it requires no prior knowledge of the probability of occurrence of the symbols to be encoded. The procedure of LZW algorithm is explained as follows. First, a dictionary containing the source symbols to be encoded is constructed. For example, if you consider an 8-bit grayscale or monochrome image, each pixel can take intensity values 0 to 255. So the first 256 words of the dictionary are assigned to intensities 0, 1, etc. up to 255. So this shows the dictionary location and this shows what is the entry. So at the dictionary location 0 corresponds to the intensity value 0. Dictionary location 1 corresponds to the intensity value 1 and so on up to 255. Now as the encoder examines the image pixels, the intensity sequences which are not in the dictionary are placed in the next unused location. Suppose the first two pixels of an image are white. That means the pixels have an intensity value of 255. In that case, the sequence 255, 255, this is a new entry of the dictionary, which can be assigned at the first unused location of the dictionary, which is 256, since the first 255 locations of the dictionary are used. So this entry is being assigned as a new entry at the location 256. So the next time two consecutive white pixels are encountered, you can simply transmit the code word corresponding to 256. So the advantage is that instead of using 16 bits to represent 2 pixels, you can use a single 9-bit code word corresponding to 256 can be used. Thus, compression can be achieved. So now we will look into an example and see how we can encode this given 4x4 8-bit image using a 512 word dictionary with the starting content as shown over here. That is, the first 256 locations of the dictionary are assigned intensity values 0, 1, 2, 3, etc. up to 255. So from the dictionary location 256 to 511, you have unused locations where you can add entries. Now we will see how this 4x4 8-bit image can be encoded using the LZW technique. So the image is encoded by processing the pixels from left to right and then top to bottom. Okay, so we know that the dictionary is a 512 word dictionary in which the first 256 words are assigned intensity levels 0 to 255. So the encoder first looks at the concatenated sequence 3939. So the encoder recognizes that 39 is an entry in the dictionary, but the sequence 3939, this is an unrecognized sequence. So the encoder, what it does is it adds the sequence 3939 at the first unused dictionary location, which is 256. So this 3939 is added as a new entry in the dictionary at the location 256. At the same time, since the encoder recognizes 39, the output of the encoder is the dictionary location corresponding to the intensity 39, which is 39. Now the encoder looks at the next sequence 39126. Again, this is an unrecognized sequence, so that is added as a new entry in the dictionary at the location 257. But it recognizes 39 as an entry in the dictionary, so the output of the encoder is the dictionary location corresponding to 39, which is 39 itself. In the next case, the dictionary looks at the sequence encoder looks at the sequence 126 126. So this is an unrecognized sequence, so this sequence is added as a new entry in the dictionary at the dictionary location 258. At the same time, the encoder recognizes 126 as an entry in the dictionary, so the output of the encoder is the dictionary location corresponding to 126, which is 126 itself. So in this way, your image is getting encoded. So in the next time the encoder encounters the sequence 3939, now the sequence 3939 is a recognized sequence because it is already added in the dictionary. So the output of the encoder is the dictionary location corresponding to the entry 3939, which is 256. The output of the encoder is 256. But at the same time, the encoder realizes that the sequence 39, 39, 126 is an unrecognized sequence. So what will happen is this sequence is added as a new entry in the dictionary. So the sequence 39, 39, 126 is a new entry in the dictionary at the next location, which is here, it is 260. So in this manner, you can encode all the pixels of this image. And How compression is achieved is the original image, it is a 4 cross 4 image, so there are 16 pixels. Each pixel is represented using an 8-bit value. So the original size of the image is 128 bits. But that is reduced using LZW coding technique. So using this coding technique, the output of the encoder, you will have 10 codes, okay, and each code can be represented using 9 bits. So the output of this encoder is simply 90 bits. So you're able to reduce the size of the image from 128 bits to 90 bits, thus compression can be achieved. Now we will look at transform-based compression. Transform-based compression is significant because the pixels in an image are highly correlated with the neighboring pixels. So transform coding is a mathematical operation that converts a large set of highly correlated pixels into a smaller set of uncorrelated coefficients. So an image in the time domain can be transformed to the frequency domain in order to minimize the spatial redundancies. So an advantage of this is that, for example, if you perform the discrete cosine transform, the energy of the transform data is mainly condensed in the low frequency region, and it can be represented by a few transform coefficients. So most of the transform coefficients can be discarded without affecting the quality of the reconstructed image. Thus, a good compression ratio can be achieved. This is the block diagram of transform-based compression. The original information is first undergoing a transformation. So here the transformation compacts the information present in the image to a smaller number of coefficients. This is then given to a quantizer, which is fed to an entropy encoder. The entropy encoder is used to remove any redundancies present in the image. Later on, this is then fed to a channel encoder. In the channel encoder, a controlled amount of redundancy is introduced to protect the information from further channel errors as it propagates through the channel. At the receiver side, the inverse operation of channel decoding, entropy decoding, inverse quantizer, and inverse transformation is performed in order to get back the reconstructed image. The steps of transform-based compression are as follows. The first one is transformation. Here an image is transformed to produce a set of linear transform coefficients, thus changing the correlation properties of the image. Now for efficient compression, the transform should have the following properties. The first one is decorrelation, that is the transform should generate less correlated or uncorrelated transform coefficients in order to achieve a higher compression ratio. The second property is linearity. Linearity principle allows a one-to-one mapping between the pixel values and the transform coefficients. The third property is orthogonality, that is, transforms should be orthogonal in nature. It has the feature of eliminating any redundancies in the transformed image. The second step is quantization. So quantization is a nonlinear or irreversible process which removes the components of transform data which are unimportant for visual information. So here the transform coefficients are truncated and rounded off, thereby reducing the number of bits needed to represent. The next block is the entropy encoder. The function of the entropy encoder is to reduce the number of bits required to represent each symbol at the quantizer output. So here the quantizer output is encoded using any of the entropy based coding schemes such as Huffman coding, arithmetic coding, or run length coding, which was discussed in the first part of the sixth module. In channel encoding, basically, it takes into account the errors that can occur when the bit stream is transmitted through the channel. So it uses techniques such as cyclic redundancy check or parity. This bit stream is then transmitted through the channel and reaches the receiver. At the receiver side, you have a decoder section. The decoder section consists of the channel decoder, the entropy decoder, the inverse quantizer, and finally inverse transformation in order to obtain the reconstructed image. Now we will look at the image compression standard JPEG. Now both the ITU and ISO in the 1980s, they established a joint international standard for the compression of grayscale and color images known as Joint Photographic Experts Group or JPEG. Now the JPEG compression standard, it can be lossy or lossless depending upon the application and the desired compression factor. The JPEG standard generally uses the block-based DCT coding. Block-based means that the transform is not applied to the entire image at a stretch, but it is applied over fixed blocks, usually of size 8x8 or 16x16. Now the entropy encoding that is used is generally run length coding and Huffman coding. Now this image compression standard is generally used for the compression and recovery of still photographic images, and it is one of the widely used standards over the internet. This is the block diagram of a JPEG encoder and decoder. An input image is first partitioned into 8x8 subblocks. FDCT stands for Forward Discrete Cosine Transform. So the forward discrete cosine transform is computed for each of the 8x8 blocks of pixels. This results in a set of transform coefficients with increasing spatial frequency. So the coefficient with zero frequency in both dimensions is known as the DC coefficient, and the remaining 63 coefficients are known as the AC coefficients. So the FDCT step lays the foundation for achieving data compression because most of the energy of the signal will be concentrated in the lower spatial frequencies. So these coefficients are then scalar quantized using uniform quantization tables. This is followed by zigzag scanning. So the purpose of zigzag scanning is because most of the high frequency coefficients will be zero after quantization. The resulting bit stream is then run length coded in order to generate another sequence, which is then later Huffman coded for transmission or storage. At the receiver side, the reverse operation of decoding, dequantizing, and inverse transformation is applied in order to get back the reconstructed image. The process of JPEG compression is explained as follows. The first step is the decomposition of picture into blocks. That is, the picture is first divided into blocks of size 8x8. The advantages of block processing is that the transform of smaller blocks is much easier to compute, and the fact that correlation between the neighboring pixels is much more than distant pixels. The second step is discrete cosine transformation. This transformation helps in the energy compaction of signals, so it results in an 8x8 matrix of transform coefficients with increasing spatial frequency, and here the DC coefficient represents the average luminance or chrominance of each block. The third step is thresholding and quantization. So coefficients below a predetermined threshold are made zero, and the remaining coefficients are quantized using uniform quantization tables. In the next step, the quantized coefficients are read using a zigzag scan. This is used to transform the matrix into a bit stream. This is followed by run length coding. So in run length coding, the number of occurrences of 0 is coded followed by the next non-zero value. This in turn reduces the number of bits needed for transmission. The next step is variable length coding or Huffman coding, in which the most frequently occurring values are encoded with a shorter code and the less frequent values are encoded with a longer code. So these two steps will help ensuring a compression factor of 2 to 3. Now at the receiver side, the decoding operation is the reverse process is being applied. That is, the data stream is entropy decoded. It passes through a reverse zigzag table in order to generate a two-dimensional array. This array is then rescaled using the quantizing factor and then passes through inverse discrete cosine transformation in order to obtain the reconstructed image. Now we will discuss the video compression standard MPEG. So the Motion Pictures Experts Group, or MPEG, is an ISO video compression standard that is used to compress moving pictures and associated sound for multimedia applications. Now the main objective for developing the MPEG-1 standard was to allow storage on a CD-ROM with a constant total bitrate of 1.5 megabits per second. So the video part uses 1.15 megabits per second and the remaining 350 kilobits per second was being used by audio. Now, video compression exploits the temporal redundancies between the successive pictures that make up a video sequence. Objects in a video sequence move in predictable patterns and can therefore be motion compensated from frame to frame. So a motion estimator uses the reference frame stored in a buffer to compare it with the current frame of the video stream and find similar blocks between them. The position of the block in the currently coded frame relative to the block in the reference frame is described by the motion vector. This figure shows how the motion estimator works. So each block in the current frame is compared with a set of blocks of the same size in the previous frame to determine which is the block that best predicts the current block. So when a best matching is found, a motion vector is determined which specifies the reference block. This figure shows the block diagram of an MPEG encoder and decoder. Since motion compensation is difficult to perform in the transform domain, the first step is to create a motion compensated prediction error in the pixel domain. So for each block of the current frame, a prediction block in the reference frame is found using motion vectors which are found during motion estimation. This is then differenced to generate the prediction error signal. The resulting error signal is then transformed using two-dimensional discrete cosine transform and then quantized using an adaptive quantizer. This is followed by entropy encoding using a variable length encoder, and finally it is buffered for transmission over a fixed rate channel. At the decoder side, the reverse operation of variable length decoding, inverse quantization, and inverse transformation is done to generate the prediction error signal. This prediction error signal is then added with the prediction block of the reference frame in order to reconstruct the block of the current frame. Now, there are two types of lossy data compression techniques. Scalar quantization. In scalar quantization, each pixel is considered independently and then quantized. It does not make use of the correlation between the pixels in an image. The scalar quantizer is generally characterized by a staircase function that relates the input samples with the output values. There are two types of scalar quantization, namely the uniform scalar quantization and the non-uniform scalar quantization. In vector quantization, your image data is divided into blocks or vectors and then quantized instead of a single sample. So this technique uses the correlation among the pixels in an image. Now we will see how vector quantization is performed. Vector quantization is a block coding technique that is used to quantize blocks of data instead of individual pixels. So at the encoder side, the input image is first divided into a set of non-overlapping image blocks or vectors. So the set of all possible code vectors or code words from the code book. So for each image block, the closest code word in a code book is found. So for a given block, the closest code word is the one that has the minimum squared Euclidean distance from the input block. The index corresponding to the closest code word in the code book is then transmitted to the decoder instead of the image block, thus achieving compression. This figure shows the block diagram of a vector quantization scheme. The input image is first divided into a set of non-overlapping image blocks. For each block, the closest code vector is found from a code book, and the index of the closest code vector is then transmitted through the channel. At the receiver side, the same code book is used in order to recover the code vector from the index. The performance of the vector quantizer is proportional to the code book size and the vector size. So as the size of the vector blocks increases, the correlation among the blocks decreases, and there is an increase in the computational complexity. So the blocks used for vector quantization are usually small. But if the blocks used are very small, there will be an increase in the number of code vectors, which is undesirable for compression. The number of code vectors depend mainly on two parameters. The rate R, which is the number of bits used to represent each pixel value, and the dimension L. The dimension is determined by the way in which the pixels are grouped. So the number of code vectors n is equal to 2 raised to r into n. So as the number of vectors in the code book increases, the search complexity also increases. So generally, vector quantization is a lossy compression technique that can be used both in the spatial as well as frequency domains. The last topic is wavelet-based compression. We will start by defining what a wavelet is. We know that a wave is an oscillating function of time or space that is periodic. So a wavelet is a waveform that is having a limited duration and an average value of 0. A function psi of x can be called a wavelet if it possesses three properties. The first one is the function integrates to 0 or its Fourier transform psi of omega is 0 at the origin. That is integral minus infinity to infinity psi of x dx is equal to 0, or its Fourier transform at the origin is equal to 0. So this first equation shows that the wavelet has an oscillatory or a wave-like appearance. The second property is that the wavelet is square integrable or equivalently has finite energy. that is integral minus infinity to infinity mod psi of x the whole square into dx is less than infinity. This equation shows that most of the energy is confined to a finite interval, that is, it exhibits a good space localization. The third property that the Fourier transform of the wavelet must satisfy is that integral minus infinity to infinity mod of psi omega the whole square by mod omega d omega must be less than infinity. This shows that the Fourier transform of the wavelet is a localized function. So since the Fourier transform is zero at origin and decays at higher frequencies, it exhibits a band-pass characteristic. The wavelet transform decomposes an image into a set of sub-images having different resolution. So it results in a multi-resolution image representation with localization both in the spatial domain as well as the frequency domain. Discrete wavelet transform is generally obtained by filtering the signal through a series of digital filters at different scales. The scaling operation is done by the process of subsampling or decimation. This block diagram shows the image compression using wavelet transform. JPEG 2000 is a compression standard that uses wavelet transform. So the source image is first transformed using a discrete wavelet transform. It is then quantized and then entropy encoded to form the compressed image. The compressed image passes through the channel and reaches the receiver where the inverse operation of decoding, dequantization, and inverse wavelet transform is done to obtain the reconstructed image. So the main advantage of using wavelet transform is that you are able to represent the image in multi-resolution representation, which is desirable for image compression. The advantages of wavelet-based image compression are as follows. Wavelets have a non-uniform frequency spectra which facilitate multi-scale analysis. It exhibits a good localization in both the spatial and frequency domain, unlike other transforms such as the Fourier transform or cosine transform, which gives good localization only in one domain at the expense of the other. Multi-resolution property is significant because the human eye has different sensitivities to the low and high frequency components of an image. So only the desired components of an image can be seen with a higher degree of resolution. Discrete wavelet transform can be applied to the entire image without imposing the block structure. This can help in reducing the blocking artifacts or noise which is seen in block-based coding techniques. Thank you.